Hello everyone, welcome back to MGF1106. In this last section of this chapter, we'll be discussing another type of argument we call the syllogistic argument, and we will see the difference between the argument we have learned so far, which is the symbolic argument, and we want to see the difference between symbolic argument and a syllogistic argument. Okay, so let's get started. Section 3.6 syllogistic argument. Okay. So we have know that symbolic argument included this is nothing but a compound statement, right? And the symbolic argument has compound statement of or and if and only if, and then if and then. All of them is the symbolic argument. Okay, this compound statement. And we use the truth table to determine if the argument is valid or invalid. Now for syllogistic argument, we're not going to have and or if and then or if and only if anymore. Instead, we will have some word over here, some word and phrases, and that you can use to tell the difference between two different type of arguments. Okay, so the word we use in syllogistic argument is all. Okay. Okay. So you're gonna see all, or you can see some. Okay. You may also see none. Okay. Okay. You're gonna see this word over here. Okay. Okay. And last time for the symbolic argument, right? The compound statement, we see only and or, and if and only if, and if and then. But now, for syllogistic argument, we're gonna use you will see this. And in order to determine the syllogistic argument valid, we have, instead of using the true false table, we're gonna use Venn diagram. Okay, so I'm gonna put over here Venn diagram to determine if syllogistic argument is valid. Okay, so for this section, so in order for you to understand syllogistic argument valid or not valid, we just jump into the example right away, and we're gonna go ahead and draw the Venn diagram. Okay, so the strategy to determine if the syllogistic argument is valid is that if we can draw another Venn diagram that contradicts to the original argument, then that argument is invalid. If we cannot find any other Venn diagram, I mean that if we can only find one Venn diagram that corresponding to the argument, then we know that that argument is valid. Okay, now I'm going to go ahead and jump into the first example right away. You will see example number 1. Okay, so I have something like this. Let's see, I can where is that? I put it somewhere. Okay. Okay, so I have the problem like this. Okay, and they ask us to use the Euler diagram, which is the Venn diagram. You can use the textbook over here. Some textbook they put Venn diagram. Some textbook they put Euler diagram. So it's kind of the same thing. So I'm gonna put over here Euler diagram. Okay, the Euler diagram. You remember last time we talked about set, right? Venn diagram, which we have a rectangle representing for a universal set, and we have a circle, right? Euler diagram, kind of same thing. They also have a table, and they have a circle. It's just the name. It's just the name, okay? I see sometimes they put the Venn diagram, sometimes they put the Euler. So most of the time, I mean, they put as the Euler diagram, but because we already know what Venn diagram look like, so I'm gonna put Venn diagram here, both Euler diagram, kind of the same thing. Okay. Okay. So let's see. Let's see if we can check if this one is valid or invalid. Okay. Okay. Um. So you see that. Let's read the first premise over here. All U.S. voter must register. Okay. All people who register must be U.S. citizen. Okay, let's draw the first circle for the first premise over here. Let's see if we can draw that. So all U.S. voter. Okay, you can draw universal set if you want to. In our textbook, they draw universal set. But in some other textbook, they don't draw universal set. So universal set represented by the rectangle is not really important. Okay, so if you want to put the universal set, that's fine. You don't want to put a universal set, it's still okay. Yeah. So I'm gonna do the first example with universal set. Then later maybe I'm not gonna draw universal set anymore because it's not really necessary. Okay, it's not really needed. So it's not really important right here. So I'm gonna draw the first circle. All U.S. voters must register. So the first circle must be U.S. voter. Okay, U.S. voter. Okay, then must register. So U.S. voter must be inside the circle representing registration. Okay, so I'm gonna put another circle in here. Oops. It's not good right here. Okay. See that there's a problem of the universal set. It's too small. We cannot draw it. So I'm gonna go ahead and delete this. This is no need. Okay. Okay. So if you want to draw the universal set, make sure your universal set must be big enough. So I have another circle right here, and this circle over here is the registration. So I'm gonna put register over here. Okay. That represents the first premise. Now the second premise: all people who register must be U.S. citizen. Okay. Okay. Must be U.S. citizen. All people who register must be U.S. citizen. Therefore, U.S. voter are U.S. citizen. Okay. So U.S. voter right over here. Okay, U.S. voter is the purple. So U.S. citizens, all people who register must be U.S. citizens. So this is all the U.S. voter over here must be U.S. citizen because all of them must be U.S. citizens. So this one must be U.S. citizen. So I'm gonna use another. So I think I'm gonna draw this really even bigger than this. You see that we don't have enough space. So I'm gonna draw really big right over here. Let's see. know what? Let's see if we can use. Let's see if we can use there's a way to draw. There's a way to draw a circle perfectly right over here. Okay, so this is, there you go. This one, US voter. Okay, then let's draw another one that is register. Okay, this register. Okay, that's big enough. So this is register. Okay. Okay, all US voter must register. So okay, register represented by this circle right here. US voter is smaller because US voter must register. Then all people who register must be US citizen. All people who register must be US citizen. I think this make it. Let me see. You can draw this smaller. Okay. You know what? I hate this. Let's draw it again. Okay, must be. Okay. So this register. Okay. All right. It's take a lot of time over here. Okay, let's do it again. So this is register. And all people who register must be US citizen. Okay, so everything over here must be US citizen. Okay, so everything. Oops. Everything here must be US citizen. So US citizen outside. So this one must be register. Register. And all people who register must be US citizens. So US citizen in here. Now, then the conclusion is therefore all US voter must be US citizen. Okay, so you see that US voter must be US citizen, must be US. So that's why US voter must be the subset of US citizen, must be inside right here. Now, the thing is that if we draw the picture like this, then we know that this conclusion over here is valid. So the whole argument over here must be valid. So this must be valid. Now, in order to show that, let's see if we can show that this argument over here is valid, is invalid or not. Okay, in order to see if this argument here is invalid, we have to check if we can draw any other case that satisfies two premises right over here, but some way somehow contradict with the conclusion. Can we draw that? I don't think so, because we draw the first two premises over here, and at the end you see that the US voter must be US citizen. There's no other option. Because those people who register is US citizen, must be US citizen, but US voter is inside register people. So of course US voter must be US citizen. This is valid. It's true all the time. We cannot draw any other case that contradict to the conclusion right over here. Okay? So that's why the argument here is valid, because, let's put over here, because due to no contradiction. In other words, it means that we can draw another Euler diagram that contradict two conclusion. Okay, we cannot draw any that order that contradict conclusion. I'm sorry, there's no two over here. I should put two. Okay. All right. So that's the first example. Now let's do another example and see the second example over here. The argument is the syllogistic argument over here is valid or invalid. Okay. How about this? Okay. Okay, like that. Okay, now again we have two premises. Let's draw the circle for the first premises. The first premise. Okay. All baseball players are athletes. Okay. All baseball players are athletes. Okay, so look like that. Okay. So all baseball players are athletes. So this one must be play baseball player, because baseball player all of them are athletes, so mean baseball player circle must be inside the athlete circle, right? Must be inside. Okay, must be inside. Somehow I cannot draw that. There you go, must be inside. This one must be athlete. Okay. Then all ballet dancer are athletes. All ballet dancer are athletes. Therefore, no baseball player are ballet dancer. Okay, they say all ballet dancer are athletes. All ballet dancer are athletes. So I can draw another circle representing ballet dancer, but inside the athlete, there's no E over here. I'm sorry. Somehow I put the wrong spelling. I can draw another circle inside here because SR is inside here. It is athlete, so I can draw the circle like this. Okay, so this one I can put ballet dancer. Okay, so this is ballet dancer, right? Because they say ballet dancer after, so must be ballet dancer inside. Now the conclusion is therefore no baseball player are the ballet dancer. Well, I have to say that over here, two circle over here is not overlapping or intersecting each other. It means what? It means that no ballet dancer, no baseball player are ballet dancer. No baseball player are ballet dancer. But the thing is this. The thing is this. If we go ahead and move this one over here, it will contradict the conclusion, right? It contradicts the conclusion. Look at that. If I draw another one, right? If I draw another one, okay, then I draw this. Then I draw another one. Okay, then you will see what I can put over here. I can put over here athlete. Then I put over here baseball player. Baseball player. Okay, then I'll put over here ballet dancer. Then you will see that the ballet dancer is also the athlete, but you see that some ballet dancer is also baseball player. You see that? Ballet dancer. Some ballet dancer is also baseball player, because you see that some of the two circle over here share in common. They share this part right over here. You share this part right over here. So you see that I can draw a picture that corresponding to the first two premises, but the thing that I also have two picture. Okay, that have two picture. I have only one picture. I'm sorry. I have only one picture that satis. I'm sorry. I have two picture that satisfy the conclusion also. So look at this. Is this one also satisfy the conclusion, right? But I'm sorry. There's only one. So one of them satisfy the conclusion. Okay, only one of them satisfy the conclusion. But this one satisfy the premises, but it does not satisfy the conclusion. You see that? It satisfies the premises. This one satisfies two premises. This one also satisfies two premises. But only this one satisfies the conclusion. This one does not. This one contradicts conclusion. So it means what? It means from here that I told you that the whole argument will be invalid if we can draw another diagram that satisfies two premises, but contradicting the conclusion. So this over here will be invalid. You know what I mean over here, guys. I mean, so let me repeat it. Okay, let me repeat it. I can draw two Euler diagram that satisfy two premises right over here, but there's only one. Okay, there's only one diagram. There's only one diagram represent satisfy the conclusion. This diagram over here satisfies the premises, but it does not satisfy the conclusion. That's why the whole thing argument over here is invalid, because we can draw another Euler diagram that does not satisfy the conclusion. Okay. Okay, let's check another one. Let's check another one. Example number 3. Let's check another one. How about this? Okay. Okay. So again, I have used Euler diagram to determine whether the following is valid or all mathematicians are logical. Okay, all mathematicians are logical. We can go ahead and draw the circle right over here. All mathematicians are logical, so mathematician represent inside. Okay, being logical represented by the circle outside. Okay, a circle outside. So of course this is satisfy the circle, the picture right now satisfy the first premise, right? So this is all mathematician. I just put all mathematician, all math logical. So this one must be logical. And they say what? They say no poet are logical. So no poet are logical. No poet are logical. So no poet logical. It means what? It means that when we draw the circle for the for poet, it it cannot be inside the circle right here, or it can overlap the the big circle right here, because they say no poet are logical. So it means that there's a whole different circle. Okay, and this one represent a poet, and you see that it's just joy set over here because we don't have any poet logical. We don't have anyone logical. Okay, so therefore no poet mathematician. So no poet and mathematician. And it makes sense because you see the mathematician over here, circle over here, and the poet circle over here is also disjoint set. It's also disjoint set. Okay, I'm sorry. I believe I said joy set before. So I said again, poet circle and logical circle over here is disjoint set because there's nothing sharing common. So poet circle and all mathematician circle over here is also disjoint set because it's nothing in common. So this is so disjoint set. Disjoint. Okay. It's disjoint. So and this argument over here, I have to say is valid because we cannot draw another picture satisfy two premises but contradict the conclusion. Okay, if we draw the post in here, okay, then it contradicts the premises because they say that no post is logical. Okay, so it must be outside, and when it is outside, and of course, poets and or math circle over here must be disjointed. Must be, and poets and logical circle over here must be disjointed. Okay, so this one, so I can conclude that this is valid. Okay, this argument over here must be valid. Okay, all right. Now let's do another example. Example number 4. You know what? I think I'm gonna go ahead and load all of them. Then we're gonna do it later. 5. Example number 5. Number 6. Okay, we're gonna do find 6 later. Okay, let's do 4 first. So example number 4. Okay. 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 Oh, okay, 4 we did. So we already did 4 too. 1, 2, 3. Is this all right? Okay, example 4. It's a little bit different. I thought I'd repeat the example, but it's not. This over here is no poets are mathematician. So all mathematician are logical. So we'll go ahead and draw that. All mathematician are logical. So this mathematician over here, all of them are logical, so must be inside. So this one must be math. Okay, math. All math, all mathematician. I just put all math. Okay, all mathematician. So over here I have a logical. And no poet a mathematician, or no poet a mathematician. So I can put what? I can put over here. So no poet or mathematician, it means the mathematician set and poet set must be destroyed. So I can draw this one over here. Okay, so this one must be poet. So you see the no poet or mathematician, so this one was destroyed right here. Therefore, no poet are logical. Oh, it doesn't make sense, right? It does not make sense, right? Because what? Because over here you see that the poets over here is logical, but they say no poet are logical. So you see that I can draw a picture that contradict. I can draw an Euler diagram that contradict to the conclusion, right? Well, I can draw another diagram over here. Look at this. I can draw another diagram over here. Okay, and another one right here. And another one. Okay, so you see that this one I put all mathematician. Okay, this one I put logical. And the one over here I put poet. You see the poet over here and all mathematician circle up here is also this joy set. This is this joy set. But you see that I can't draw another Euler diagram, which is this one over here, that contradict to the conclusion, because you see they say no poet logical. No poet are logical, but now I can draw an Euler diagram that is say that poet are logical. This one, no poet are logical, because this poet and logical set are disjoint set. But now I can draw a case when poet are logical. So this is invalid argument over here. Okay, so this is invalid. Okay, invalid. Okay, example number 5. Okay, it's the one right over here. Okay, all mathematicians are logical, so kind of the same thing. Same topic. All mathematicians are logical, so all mathematicians are logical. So this is logical set right over here. Is logical. Mathematician must be inside because they say all of them. Okay. So this is mathematician. All mathematician. Okay, all mathematician. Some poets are logical. Okay, some poets are logical. Let's draw another one. Some poets are logical. Okay, so poet over here. Therefore, some poets are mathematician. Okay, so look like that my picture over here, my Euler diagram will be satisfied two premises and also satisfy the conclusion, because some of them are mathematicians right over here. Okay, right over here, some of them are mathematicians. But the thing is this, the thing that I believe that I can draw another picture. It contradicts to the conclusion. So this is logical. This is all mathematician. So this satisfies the first premise. Some poets are logical. Okay, some poets are logical. Okay, so this poet. But if you notice, you see that all mathematician set and poet set are disjoint. But they say over here that some of them are mathematicians. So you see that this disjoint over here, it contradicts to the conclusion over here. So it means the conclusion over here is not always true. It's not always true. That's why the argument over here is invalid. Right? The argument must be valid if everything is true, right? Everything is true, but now you see that this is not always true, so that's why this one invalid. Okay. Now let's do the last example right here. Oops. Let me erase this. Example number 6. Okay. Okay. All mathematicians are logical. Kind of same thing. Okay, let's run again. So I have again I have two circles. So this is logical. This are all mathematician. Okay, all mathematician logical. Euclid was logical. So Euclid is just an element. So Euclid is logical associated. Therefore, Euclid was mathematician. Okay, so Euclid are logical. So let's draw the Euler diagram that satisfies this first. The conclusion and satisfy the own premises over here first. So Euclid were logical. So here. So Euclid was logical. So Euclid is inside logical, but also inside the mathematician circle. So look like that over here, the whole Euler diagram here satisfy everything. But the thing is, I can also put the Euler outside here. Look at that. I can put Euler outside here. Okay, so this is logical. Logical. This is all mathematician. But Euler I can put over here. So it means what? It means that Euler is not always mathematician. Over here they say Euler was mathematician. It might, but it might be not. Because over here Euler is not mathematician, but Euler is still logical. So this is not true. This argument is not true. It's not always true. It's true here, but we can draw another Euler diagram that contradicts to the conclusion. Okay, so this is not true, and that's why this is invalid. Okay, that's invalid. Alright, so let's jump to the conclusion. Okay, based on this 6 example over here, what we learned? We learned that if we can draw another Euler diagram, okay, that contradicts to the conclusion, then the whole argument is invalid. Okay, so I'm gonna put right at the end of it. Actually, I say that so many, at least 6 times, right? In each example, I already say that, but I'm gonna just go ahead and put it over here at the beginning, so that when you do the first example, you know how you think, the way you think logically, okay, to do this type of question. Okay, so I'm gonna put over here, I'm gonna put that if you can draw another, okay, another Euler, actually I said over here already, diagram contradicting conclusion, okay, then that argument is invalid. There you go. Okay, okay, it's not really that bad, guys. It's not really that bad. Okay, therefore statement is conclusion, so that everything is this is the premises, the second premises, the second premise, this is the conclusion. Okay, all right, so I'm gonna stop the whole chapter of logic over here. Again, watch the video carefully. If you don't understand anything, just let me know. Then if not, we'll be jumping to the new chapter in next video. Okay, I'll see you next time. Bye bye.